Hello, everybody. Thank you for joining us at the Quantum Computing Summer School lecture series this morning. It's my pleasure to introduce Elizabeth Crosson, who is a scientist working at the intersection of adiabatic quantum computing and computational complexity. She did her PhD at physics at the University of Washington, a postdoc at Caltech, and now she's an assistant professor at UNM, which is just down the road from Los Alamos. Like our other lectures, please put any questions you have into the chat and I will relay those to Elizabeth. Take it away.
Okay, thank you very much. I'm excited to give this lecture, and I want to encourage everyone to ask me questions through the chat for clarification or even just to slow me down if this material is unfamiliar. Okay, so as a starting point, many of you are probably thinking about quantum circuits. Today's lecture is going to be about the Hamiltonians that generate those quantum time evolutions. Okay, so as we know, the energy of a quantum mechanical system is an observable that corresponds to a Hermitian operator called the Hamiltonian. So the Hamiltonian H generates the time evolution of a quantum system according to the Schrödinger equation. And of course, H is a Hermitian matrix. It'll be equal to its own conjugate transpose. So, you know, for most of today's talk, we won't be thinking so much about the unitaries, but the Hamiltonians that generate them. And specifically, I want us to think about many body Hamiltonians. So what this means is that we have a quantum system with n interacting particles. So and we're going to think of the regime where n is large, maybe tending to infinity. You know, we know quantum mechanics can already be difficult to solve, even for something like a helium atom that only has 2 fermions. It could be, you know, we don't know how to have an exact solution to that case. And yet we're going to be even more ambitious, and we're going to consider this large number of particles because we want to be able to describe, say, real materials that consist of many particles. Okay, so we know from the axioms of quantum mechanics that the full Hilbert space, when you have many particles, is a tensor product of the single particle Hilbert spaces. Taking this limit, n goes to infinity, is called in physics the thermodynamic limit. And when we try to make statements about this large number of particles limit, it's really helpful to use this big O notation. We say that some function, g of n, is O of f of n if for all sufficiently large n, so as n goes to infinity, g of n is no larger than a constant times f of n. Okay, so the precise meanings of these notations, right? So the big O of f of n asymptotically no larger than f of n, and the big omega f of n is asymptotically no smaller. So they give you upper bounds and lower bounds on quantities. Okay, so many body quantum systems in general are extremely complicated. Now, if they are in thermal equilibrium at a low temperature, right, where their properties, their quantum properties are going to be most pronounced, then we can study sort of the part of the system. The aspect of the system we want to study are the ground states, the states of lowest energy, because those have the most pronounced quantum behavior. So of course the energy, the ground state is just going to be an eigenstate of the Hamiltonian. Here, this rho of beta is the quantum thermal state, the quantum Gibbs state. And we can think about as the inverse temperature goes to infinity, the temperature goes to 0. This quantum Gibbs state will just be a mixture of states that are in the ground space, the lowest energy states. And typically without symmetry, the ground state will be unique. Okay, so Another simplifying observation, so I just argued that we're going to focus on ground states when we're doing this many body physics. Now, another big simplification is that the interactions we most want to study tend to be few body. So the interactions themselves involve a few particles at a time. So for example, you could think of a classical system of many charged particles. And if you're in the regime where you can use electrostatics, then the interactions may be governed by Coulomb's law. And Coulomb's law then describes a potential between two charges at a time, even though you have n of them in total. And so to get the total energy, you would sum over all of those interactions. Okay, so we define the terminology we use is that the Hamiltonian is k local, where each interaction term acts on at most k subsystems, say qubits, individual particles in this case. And we typically want to have this k be O of 1. So if you think about what the big O notation means, k should be a constant as n goes to infinity. Okay, and so when we write a local Hamiltonian like this as a sum of these HA terms, if each of these say acts on 2 qubits, but the entire Hamiltonian acts on n qubits, well, you can't just add up a bunch of 4 by 4 matrices to get a 2 to the n by 2 to the n matrix. So what this notation means is, well, we kind of leave an implicit identity term, right? So the HA part acts on at most k of those subsystems in the tensor product, and the rest of them are acted upon with the identity. Okay, and these identities are left implicit to simplify the notation. Okay, so the word locality is overloaded in the programming sense. It means different things in different communities. So I just told you that Coulomb's law was too local because it acts on 2 particles at a time. But of course, we know that Coulomb's law also acts on particles that are spatially separated, decaying with the square of the distance. So to be more precise, we want to distinguish between spatial locality, or a spatially local system, and this more general notion, which is sometimes called combinatorial locality. So how many particles are involved in each interaction? So for a spatially local system, we want the interactions to actually be confined to a ball in Euclidean space of some constant size radius. And spatially local systems then are important in the quantum descriptions of matter, crystals, magnets, conducting metals, because often these involve our particles, which may be spins, qubits, bosons, fermions. They're interacting with near neighbors on a lattice. So when I draw these diagrams, the line indicates interactions, say, between 2 qubit particles. But we can also consider these more general kinds of connectivity where the interactions are long range across space, but still involve only a few particles at a time. And so here's a graph where the red dots are vertices and the black lines represent interactions. And as you can see, these interactions wouldn't embed in some low dimensional space, and yet this Hamiltonian is still what we call K-local. And one justification for these combinatorial Hamiltonians, local Hamiltonians that are not spatially local, is that we can simulate their time evolution using a quantum computer. So in other words, this system represented by this graph may not actually be some lattice in space that represents a real material, but it is a quantum system whose properties we can investigate with a quantum computer. Okay, so let's get some examples of local Hamiltonians. So the first example is the classical 1D ferromagnetic Ising model. And it describes a chain of spin 1/2 particles, or if you like, just classical spins that are up and down on a line where the interaction favors alignment along the z direction. Okay, so I'm using some quantum notation, even though it's a classical model. I think it's probably familiar to most of you. So, okay, so here we just have the interaction between particles that are nearest neighbors, I and I plus 1. And this will be minimized. The minimum energy corresponds to them being aligned. And so the ground states we can determine by inspection. And the ground space then is the span of the all 0 string and the all 1 string, because those are the product states that minimize the energy of this Hamiltonian. So this is essentially a classical model. All the terms commute. They can be simultaneously diagonalized, and it's easy to get this solution, right? But we can make this a lot more interesting, say by adding a transverse field in the x direction. And then these terms no longer commute. And so this is called the 1D ferromagnetic transverse Ising model because of this transverse field. And it's certainly more distinctly quantum. The ground state is highly entangled, so it's not a product state. And the analytical solutions are highly non-trivial, developed in the 50s and 60s. They're major milestones in mathematical physics. So, you can check the textbook solution for the ground states of these models, but it takes several pages. It would take a whole lecture. So I just want to put that out there as an example of how quickly things get much more complicated. But there is kind of a model that we can analyze easily here. So this is a 1D spin model. So again, the interactions will be between nearest neighbor qubits. So 1D spin models are often called spin chains. This particular one is called the ferromagnetic Heisenberg model. And it was introduced as a model of quantum magnetism. So you see here, the interactions are basically these dot products between the angular momentum operators. So if you expand it in terms of Pauli operators, this model looks like this. Okay, so you have interactions along the x, y, and z directions, all of equal strength between these nearest neighbor qubits. So discussing a bit the solution to this model, so we can form this magnetization operator that checks the z spin of every qubit. And a calculation you can do is that this magnetization in the z direction commutes with the overall Hamiltonian. And so that symmetry helps you to solve this problem. And then our intuition that we got from the Ising model about spins wanting to align suggests that ground states of this model will maximize the sum of the total angular momentum. So if you kind of, if you've done quantum mechanics of angular momentum and you combine these facts, then you might see that the ground space is the symmetric subspace spanned by these states. So let me explain this notation. So this index m ranges from 0 up to n. And for each m, what we have here, ignore the normalization. We have the sum over n-bit strings. So x is an n-bit string, but we're summing over qubit states described by those strings, such that the Hamming weight of x is some specific value m. Okay, and that's because of this property here, this commutation property that these are the states of fixed Hamming weight also have a definite value for this magnetization in the z direction. Okay, so this is the ground space then is spanned by these states. And you can see that, for example, if we take m, just to explain the normalization, right? If you have the set of strings of length n that have m ones in them, because that's what the Hamming weight is, then there's n choose m of those. So that's why this is the normalization factor. And you'll see that in this ground space, so if, say you take the case m equals 0, so the Hamming weight is 0, well, then this just reduces to the all 0 string. Or similarly, if the Hamming weight is n, this just reduces to the all 1 string. And those are product states. But if you take, say, m equals n over 2, this magnetization is n over 2, then the ground state at that point that has n choose n over 2 ones in it is going to be highly entangled. And so, we can start to see the emergence of those more complicated quantum states. Okay, Oh, and maybe one more thing is, I kind of hand waved about intuition, but once you have this ansatz, you could say plug it in to the Hamiltonian and convince yourself that way that it minimizes the energy. But analytical solutions, okay, and just to appreciate, here we had n interacting particles. The interactions were not weak. We didn't need perturbation theory. There was this big simplification from symmetry, but this is, convinces you it's actually possible to solve these n particle systems in a quantum regime. But these analytical solutions are rather rare. So this motivates us to use classical and quantum computers to find ground states. And the field of Hamiltonian complexity is really about the difficulty of finding ground states with using a computer, and we're going to characterize it with these theoretical tools from computational complexity. Okay, and so to set this up, we are going to describe a formal model of computation that allows us to describe the asymptotic time and space requirements, this big O, big omega type notation, to solve these problems. And we'll also discuss the formal idea of a computational reduction. So this is, when is one problem at least as hard as another problem? Say, finding ground states of these Hamiltonians is as hard as doing this other problem, right? And so using this notion of a reduction, we can define complexity classes you've probably heard of, like P and NP, but we'll actually give precise definitions of those. And we'll relate the hardness of these local Hamiltonian problems, finding these ground states, to other problems that are, say, totally appear totally distinct from quantum physics. Okay, so to get there, I want to talk a bit about these constraint satisfaction problems. So let's consider, and then this notation will also be pretty important to us throughout this first part of the lecture. So let's consider some collection of Boolean variables here, S1 through Sn, where each Si, again, is just a bit. We can think of, when the bit is 1, that's true, and when the bit is 0, that's false. So to form statements out of these Boolean variables, we can connect them with Boolean functions like and, or, and not. So for example, S1 and S2 is true if S1 is true and S2 is true. Otherwise, it's false, right? Because this statement requires them both to be true. If it's S1 or S2, so flip this thing around to get an or symbol, then that's true if either of them is true. Okay, and so any of these Boolean functions can be described by what's called a truth table, a list of their inputs and outputs. And you can imagine combining them to make more complicated propositions or statements. So Si and Sj, either this has to be true or that has to be true in order for the overall statement to be true. And okay, so a generalized SAT problem, or a Boolean constraint satisfaction problem, a CSP, asks us to decide whether there exists, oops, this little exist symbol, I guess got, sorry, maybe you guys can see it, this existential quantifier should be there, sorry for the formatting issue. An assignment, so yeah, does there exist some assignment to these Boolean variables that makes a collection of propositions true simultaneously, right? So does there exist S1 through Sn such that, so here R sub I acts on K of these variables, which is going to be similar to our K local notion, right? So here, call this a clause, R sub I, right? And it acts on K of these variables, and it's some statement about, these two should be true and, or this should happen, right? It's just some general Boolean proposition. And then we're asking whether all of these propositions can be simultaneously satisfied for some assignment of these variables. Okay, so that's a generalized set problem, and you're just required to decide whether it's true or false. There's maybe this is just a technical detail, but if each Ri is an or statement, involving variables and their negations. So you have you're taking the and of a bunch of clauses, but each one of them is just a sequence of or functions. This is kind of like a standard form for Boolean propositions called conjunctive normal form. And the reason I mentioned that is because you have to be in this CNF to have what's called KSAT, which again might be familiar. But today, just to kind of simplify some details, I'm going to focus on this generalized SAT. Was there a question in chat?
There was. So Jacob is asking, what's the difference between a clause and a constraint, or are they the same?
They are the same. So they are the same in this particular language. I should point out that, if you're, so this is the terminology that is used, but we're going to also talk about violating constraints, which in other contexts, you might not want to consider violating constraints, but here we will. So it's a little different, say, than constrained optimization, where you would never want to violate those constraints. You'd just be outside the valid solution space. These are like constraints that you attempt to satisfy, or you tell if they can all be satisfied. But mostly they're synonymous clauses and constraints. Okay, so we can express these Boolean formulas using our notation for quantum systems. So each of these Boolean variables, 0 or 1, we can associate a qubit state, right? Ket 0 or ket 1. And what we're going to do is we're going to construct a Hamiltonian with one local term, hi, for each clause ri in the Boolean formula. And we want to map satisfying assignments, so to low energy states. So if all the clauses are satisfied, or if clause ri is satisfied, we want the Hamiltonian term hi to also have energy 0. And okay, so if we have a 3-sat problem, so each clause is just a sequence of ors. So what this does is it effectively forbids one configuration, right? So this clause here will be true if if this is true, or this is true, or this is true. So the only way to make it false is if, the first one is false, and then the second one is negated. So, that would be true, but then its negation would be false. And then if the last one is false. So this guy is satisfied as long as we're not in this state 0, 1, 0. And so we want to add a higher energy to states that violate that clause. So to do that, we can just write a projector that assigns energy 1 to that particular 3-bit string. And right, so this notation indicating which qubits we're acting on non-trivially, and of course it'll be tensored with an identity on the rest of the qubits, because that clause is only checking those 3. Okay, so now so if you had a Boolean formula that wanted several clauses to be satisfied simultaneously, then you could map it to a Hamiltonian where you wanted all of the h sub I to have energy 0. So in general, if you look at the evaluating this Hamiltonian on just a bit string, diagonal in the computational basis, then it will just count the number of violated clauses corresponding to that assignment. And the ground state energy of the full Hamiltonian is 0 if and only if the formula is satisfiable. Okay. So these Boolean connectives and/or not also form a universal set of logic gates for classical Boolean logic circuits. And so here, let's think of a circuit where you have these inputs, x1, x2, y1, y2, and they go through these gates, right? So A and B mark intermediate outputs of these logic gates, and then C would be like the output of the entire circuit. Here, universality means that any Boolean function can be expressed using Boolean circuits made out of these gates. And if the overall circuit outputs just a single bit at the end, then we'll call it a verifier circuit. And so the formal model of classical computation that we consider today is based on these verifier circuits. Instead, maybe some of you have seen Turing machines, just because these circuits generalize more naturally to the quantum setting. Okay. So we're building up to these formal definitions of computational complexity classes. So, you may have heard that P is the set of problems that can be solved in a time that scales polynomially with the size of the problem description. So let's kind of make that formal. Okay, so this is also kind of associated with our notion of problems that can be efficiently solved. So we need to first define our notion of what a computational problem really is precisely. And to do this, we use the concept of a formal language. So the definition of a language. So consider an alphabet sigma, which for us will just be a Boolean alphabet. And then sigma star is the set of all strings of any length formed by the letters of this alphabet, right? So this union over all possible strings, and any subset. So it's kind of key that there's actually infinity appearing here. So now a subset of this infinite universe of strings is called a language. Okay, that sounds extremely general. It's just some set of strings, basically. So, but they would be associated with some meaning. So, for example, a language could be the set of all 3-sat instances with a satisfying assignment, or the set of all local Hamiltonians with a ground state energy 0. And of course, they're strings, so they're describing the objects in that set. Okay, so language is a set of strings. Now, another definition we need is the idea of a uniform family of circuit verifiers, which I'll just call a circuit verifier for short. So what this is just a set here of Boolean circuits indexed by R, where R is a natural number. And each circuit then has size R, so the size is the number of gates in the circuit. And the output of each of these verifier circuits is a single bit, like we just discussed. And that single bit represents yes or no, or accept or reject. And then the third one is a little tricky. Maybe you'd need a Turing machine to define it precisely, but there's a simple rule to go from the pattern of gates in VR to those in VR plus 1. And the reason for rule number 3 is just to prevent us from embedding the hardness of a problem in the computation of the circuit itself, right? So what it means, okay. The other thing is that this subscript R that represents the size of the verifier is going to vary as we consider different possible complexity classes. Okay, so now we're ready to actually define the class P of problems that we can solve in polynomial time. So what P really is a set of languages. And a language is in P if there exists some polynomial, lowercase p, and some verifier family, okay, such that if X is in the language, then a verifier with circuit size that is polynomial in the length of the string X will output 1, right? And if X is not in the language, then our family of verifiers whose input size and circuit size are related by a polynomial will output 0. So what this is really saying is that the circuit verifiers recognize the language, right? And because the size of these circuit verifiers is restricted in this way, that's what makes it the class P of problems that are solved in polynomial time. And okay, so just some background on this, right? So P is we regard these as efficiently solvable, even though, of course, the polynomial that relates the input size and the circuit size could be huge. It could be like have a very large degree, like n to the 100, which is not really going to run efficiently in practice. But so there's kind of two justifications for this definition. So once a problem is known to be NP, subsequent optimizations can often lower its runtime. So maybe you start with n to the 100, but then people work on it and bring down that exponent. But also remember, we're trying to make precise statements about extremely difficult to solve problems. And so abstracting away from these details, like just saying the degree is allowed to be any constant, allows us to make more progress with the theory. Okay, so now we turn to the class NP, and the name stands for non-deterministic polynomial time. And so informally, NP is the class of problems with efficiently checkable proofs, even if those checkable proofs may be hard to find. So for example, if a 3-sat instance is satisfiable, then a description of the satisfying assignment is an efficiently checkable proof that indeed it's satisfiable, right? You're given the Boolean string, you plug it in, you check each clause and see that it's satisfied. Okay, so that argues that this problem 3-sat is in NP. And similarly, if you're looking at some positive integer and you're asking the question, does it have a prime factor less than m, or just a factor less than m, then that is a problem who's with an efficiently checkable proof, right? So you may not be able to find that factor, just maybe brute force searching takes you too long. But again, if you somehow are given the factor, then you can just do division to efficiently check that the answer to that problem is yes. And so for the class NP, it doesn't matter where this proof that you check comes from, only that it exists. And so sometimes actually people use the language that the proof comes from a wizard who hands you a string, a witness, to help you see that a fact is true. Okay, so that's the intuition. Let's now do the formal definition here of NP. So languages in NP, if there exist these polynomials P and Q and a verifier family, okay, so such that any problem in the language, right? For any problem in the language, there exists some string y, which is the witness, which has length polynomial in this description, the length of the description of the problem x, and there's a verifier whose circuit size is polynomial in the description x that takes as input both x and the witness y and outputs true, right? So there is some witness that allows this verifier family to recognize that x is in the language. And then the second part is crucial as well, that if x is not in the language, then for all witnesses of this length, the verifier family will not accept, right? It'll reject. And so this second case means that the verifier cannot be fooled or cheated by a false proof, and that's crucial to making this interesting. So, consider a 3-sat problem. If it has a satisfying assignment, then Merlin, the wizard, that's his official name, can give that assignment to me, and I can check it in polynomial time. But if there is no satisfying assignment, then there's nothing he could give me that would lead me to falsely conclude that the formula is satisfiable, right? I'll find a violated clause. You could run through the same argument with the integer division, right? So, you ask this question about a factor less than, say, r. Merlin gives you some number and you check it with division. But if there is no factor, then there's no way he's going to trick you that there was one. Okay, so it's not the case that we just believe everything the wizard says, because then there would be nothing interesting about this. Okay, so just from those definitions, we see that NP contains all the languages in P, because there's already a polynomial size family of verifier circuits, and it doesn't matter what witness you plug into them. But some of the problems in NP, like 3-sat, are believed not to be in P. perhaps this is unsurprising since, the class P doesn't have this all-powerful wizard assistant. It seems like we should be able to do more with such an assistant. So therefore, we have this conjecture that P is not equal to NP. Those two sets of languages differ from each other. And this is one of the greatest unsolved problems in modern science, right? There's a $1 million prize for a correct proof that P is not equal to NP. And one thing I like to point out is that the people offering this prize money won't even look at a claimed proof of P equals NP. It's considered so unlikely to be the case. Okay, so complexity theory is full of these kinds of conjectures that are strongly believed, easy to convince ourselves of intuitively, but we just don't have the mathematical technology to prove them. So kind of a stronger statement that sometimes gets confused with NP is what's called the exponential time hypothesis, that says that any classical algorithm for solving KSAT with k greater than or equal to 3 takes time, 2 to the constant times n. And in fact, there's a strong exponential time hypothesis that says as n goes to infinity, this constant in the exponent tends to 1, right? So this strong exponential time hypothesis basically says it takes exponential time to solve 3-SAT. And that is, or to solve KSAT above some fixed constant k, and that you can see as a stronger statement than P not equal to NP, right? Because if it takes exponential time for a classical deterministic algorithm, then the problem can't possibly be in P. So this strong ETH is even stronger than P versus NP. Okay. Now, since this class P includes a lot of languages that are easy to recognize, like the ones in P, or NP contains easy to recognize languages, we want a way to talk about the hardest problems in NP. And to do that, we introduce a notion of reducing one problem to another. Okay, remember, our problems are actually languages. And so what a reduction is just an efficiently computable function that maps us from problems in one language to problems in another language. Okay. So, this might look like, well, so for example, we gave this connection between 3-SAT and this version of Hamiltonian problem. And of course, those two were closely related, but technically they are different problems. Okay, and if you examine this precisely, it's really crucial that the language B is an efficiently computable function itself, which might sound circular, but of course you can get rid of that and make everything tidy. All right. So a language is called NP hard if every language in NP is efficiently reducible to the language L that we're calling NP hard. And so, informally, if a problem is NP hard, then it's at least as difficult as all of the problems in NP. But we can also have problems that are NP hard and are not themselves in NP. And an easy example of this is that we can define the complexity class NEXP, which is just like our definition of NP, but the witnesses and verifier circuits can now be exponentially large. And you can actually prove that NP is not equal to NEXP. So NEXP is a strictly more powerful class, but of course it contains everything in NP, because if you have polynomial-sized witnesses and verifiers, then those would also be in NEXP as well. So there are many problems in NEXP that are NP hard, but those problems in NEXP aren't really representative of problems in NP. And so what we're most interested in are the NP hard problems that can also be solved in NP, and those languages are those that are called NP complete. Now, from these definitions so far, it's not obvious that any NP-complete languages exist. So remember, it needs to be as hard as everything in NP and also in NP itself. And so, but you guys have sure have heard about NP-complete problems. And where those all come from is what I'm going to discuss next, which is called the Cook-Levin theorem, which is the proof that 3-sat is NP-complete. Or actually, we're going to prove today that generalized sat is NP-complete. And basically, every NP-complete problem you've ever heard of is then reduced to 3-sat. And I want to explain the core idea that connects this constraint satisfaction problem to this idea of non-deterministic computation with a witness, right? Reflect for a moment on how different those two sound on the surface. Okay, so here's how it works. So suppose some language is in NP, right? We want to give a reduction to solving a generalized sat problem. So for each X in the language, there should be a satisfiable, what does that reduction mean? So for each X in the language, there should be some satisfiable sat instance. And for each X not in the language, this function, the reduction, should map it to an unsatisfiable sat instance. Okay, so the idea is, right, so a language in NP, what are we kind of given as the assumption? Well, it means that there's some uniform family of circuits that takes in the input and the witness and, accepts or rejects appropriately. So for each gate in the circuit describing that verifier witness, we're going to write down a Boolean function on the inputs and outputs of the gate that is true if and only if the gate operated correctly, right? So here's a correspondence between a logic gate and the corresponding Boolean formula where this connective if and only if, right, is true if both sides are true or both sides are false. So these logic gates are being enforced by Boolean propositions. And the Cook-Levin proof is based on using these propositions to enforce the history of this valid classical computational circuit. Okay, so here's the idea. So let's suppose that the state of a circuit at time t is just described by some bit string, right? We've gone through several sets of gates, and now we're at time t. So we're somewhere in the middle of the circuit. And let x sub ti be the state of the ith bit at that time. So now you have two bits, x sub ti and x sub tj, that are going to pass through a gate at time t. And then the output bit of that gate should be determined by the input bits. So there's going to be some Boolean proposition R that looks like this, right? And its truth value determines whether the gate operated correctly. And we want all of the gates to operate correctly, so we're going to connect a bunch of these R's with the AND connective. And the reason that KSAT is NP-complete for k greater than or equal to 3 really comes down to this fact that these universal circuits need gates with at least 2 inputs and 1 output. So the clauses are going to enforce the correct operation of all the gates in the circuit, and also enforce the initial state to be, the input that was given, right? Because we're going to map each x in the language to a constraint satisfaction problem. But what about the part of the input that corresponds to the witness y, right? That is kind of unconstrained. What constraints do we write down there? So this whole deterministic part of the circuit is a proposition, right? It asks for the statement about all these sort of time steps of the computation, that should all be true simultaneously. But the non-deterministic part, this witness, you're really asking whether there exists some witness that you would plug into the Boolean formula describing the operation of the circuit that would make it the overall proposition true. And this quantifier, as we saw, is what really makes this a SAT problem. So the search for an acceptable witness is the same as the search for a satisfying assignment. And that's the Cook-Levin theorem. Okay, so it's a little bit abstract. Here's kind of like an example. So let's imagine that we have this circuit. The inputs that were given are X1, X2, and Y1, Y2 are the witness inputs, and those are unconstrained. So the formula you would write down for this circuit, does there exist some witness on these 2 bits? And then you would ask for the correct operation of the gate, right? So Y1 or Y2 is true if and only if A is true. And you have some clause that describes the operation of this gate. And then finally, some other clause that describes the operation of the last gate. So this connection between non-deterministic circuits with existential input, or does there exist a witness, maps to these satisfying formulas. And this is also a good example of why we define the class P in terms of polynomials of where we kind of just ask there to be some fixed degree, but we don't specify it, right? So if you think about it, the input had size X, this input here, and then it runs for some amount of time that scales polynomially in the input. So when we build this SAT formula, how many variables and how many clauses does it have? Well, it's got more variables in it, right? Because we needed variables to represent all those intermediate time steps. So that's a natural polynomial blowup or polynomial factor that increases the size of the problem in our reductions. So once we know that 3-SAT is NP-complete, you can find a bunch of other NP-complete problems by just reducing them to 3-SAT or generalized SAT. And this theory of NP-completeness was developed in the 70s as computer scientists realized these connections between combinatorial problems that did not appear to have efficient algorithms, but did have concise, efficiently checkable proofs. So just some examples of some of these algorithms. So subset sum is an NP-complete problem where you're given a set S of integers or n integers, and you decide whether there is a subset of them whose elements sum to 0. K coloring is NP-complete for k greater than or equal to 3. So a coloring of a graph is an assignment. So you have n vertices, and you want to assign one of k colors to each vertex in such a way that no 2 vertices sharing an edge have the same color. Max cut, it's popular in the quantum optimization community, is another NP-complete problem. And the max cut of a graph is the subset of vertices that maximizes the number of edges leaving the set. Now, just to say this, right, everything we described were decision problems. And so to phrase this as a decision question, is there a subset that cuts more than m edges? You'd have to phrase it that way to be NP-complete. Now, factoring is an example of a problem that is in NP. It's believed not to be NP, so we don't think we have an efficient algorithm, but we also don't think it's NP-complete. And there's theoretical evidence for this, that factoring shouldn't be NP-complete. And another problem like this, another kind of problem of intermediate complexity where it seems to not be NP, but is also not NP-complete, is graph isomorphism. So deciding whether 2 graphs are isomorphic, it's in NP because Merlin can kind of give you the description of how you would map the vertices of one graph to the vertices of another so that you could check it's isomorphic. But it's, it's not believed to be NP-complete. Now, P also has complete problems, and those just tend to look like things that are straightforward. So evaluating a Boolean proposition when all the variables are literals is P-complete, kind of by that circuit argument I just gave. Kind of whimsical here, as humans, we try to solve special cases of NP problems using creativity or luck to find the witness. And if P was equal to NP, an astounding consequence is that creativity itself would be unnecessary. We could prove all provable theorems by just turning the crank and plugging and chugging for polynomial time. Right, because mathematical proofs are something you need creativity to come up with, but once you write them down, sort of anyone could potentially check them efficiently. Okay, so setting up for part 2 of the lecture here. So solving 3-set is as difficult as solving any problem in NP. And we saw in the beginning of this lecture that any 3-set instance can be expressed as a local Hamiltonian problem, right? These Hamiltonian, we can map a 3-set instance to a Hamiltonian that is actually diagonal in the Pauli Z or computational basis. And it's a reduction because the 3-set formula is satisfiable if and only if the Pauli Z Hamiltonian has ground state energy of 0, right? And so, so that tells us that finding quantum ground states is already at least as hard in the worst case as performing non-deterministic classical computation. But what if I have a general quantum Hamiltonian? What polynomial size bit string should I use? Or what polynomial size bit string could the wizard Merlin give to me to convince me that the ground state energy is, let's say, 0? You know, if it would say that transverse Ising model with an entangled ground state or something even more complicated, right? You can't just describe the ground state by a single bit string, or at least that's what we believe. So we believe that for some entangled ground states that there shouldn't exist such a bit string. And this means that NP, while it's very powerful, you know, is not all powerful. You still need to receive classical information and check it classically. And there's quantum problems, quantum ground state problems that we believe do not fall into that framework. But so we can characterize the hardness of the local Hamiltonian problem in general, finding ground states, by relating it to non-deterministic quantum computation. So quantum circuits that accept or reject based on whether a witness exists. And that will be the goal of the part 2 at 11 o'clock today. So I'll stop there if there are any questions.
Thank you very much. You're getting a virtual round of applause. I'll kick off the questions with going back to when you were introducing the ZZ half-spin model. You made a comment that said, you know, this is kind of easy to represent because there isn't entanglement. But we know, and then that use that as motivation for the transverse field model. But we know things like, you know, max cut can be encoded in this ZZ Hamiltonian. So could you maybe refine the statement, like about, for this very simple Hamiltonian?
Oh, absolutely. So I really meant just this exact ferromagnetic. Okay, so what makes this problem easy in general is the ferromagnetic nature of the interactions. The fact that Zi and Zi plus 1, or you could think it more generally, this could be a I plus 1 could just be a J here. But as long as you have this minus sign in front of every term, that tells you that the spins want to align. So if you had a bunch of these 2 local ZZ terms and they all had these minus signs, you would still know that that you should have this all zeros or all ones. Now, the case of max cut actually corresponds to everything having a plus sign. You draw a ZZ for each edge in the graph, but you put a plus sign because the spins actually want to disagree. You want, you know, your ground state counts, you know, the vertices that are assigned 1 are in one subset and the vertices assigned 0 are in the other. And you want to sort of maximize the edges between the 2 subsets. So yeah, changing this minus sign to a plus makes all the difference when you're on a more general graph. Now, of course, if you're still on a line, zi plus 1, and this was a plus, then you could still determine the ground states by inspection, 0, 1, 0, 1, 0, 1. But on a more general graph where you would have, say, frustrated triangles, that would no longer be possible, and you would run into these very hard cases because it's an NP-complete problem. And just one more thing to say there that reminds me to say is that all of this stuff about NP completeness is about the worst case of hardness, right? If you had to solve max cut on a path graph, well, that turns out to be easy. So you have to consider worst case graphs that are out there.
So does that imply that something like breaking up the Hamiltonian into subparts is how feasible that is connected to the complexity of the input structure?
Yeah, exactly. You can use this kind of divide and conquer strategy where you maybe try to solve the problem in one subsystem or another, then in the worst case, though, you will sort of violate all the constraints that connect the two subsystems.
Yeah.
Right. But yeah, even within these NP complete problems, you can certainly find cases that are easy. It's only the worst cases that are hard.
Absolutely. Other questions from the audience? I'm not seeing any in the chat, so I will ask another of my questions. So you mentioned this idea of asking, does this Hamiltonian have a ground state of zero energy? That equates to basically proving that this formula is unsatisfiable, right?
Well, the ground energy, or I guess it's a convention, but the way I set it up is that the Hamiltonian terms count the violations. So ground state energy 0 is the case where the formula is satisfied, at least in this mapping from 3-sat to local Hamiltonians. So the ground state energy 0 case is the case where none of the constraints are violated.
Right. Yeah. So in the classical sat solving world, there are producing the witness is great, right? Because you can very quickly check that you have this valid witness. It's the proof that there exists no valid witness that is usually a big burden. Well, maybe that's a gross simplification, but let's say this is a hard problem. And I'm wondering if we rephrase that question of build a Hamiltonian and then provide some kind of analysis to say, I can guarantee you there has to be more than one violated constraint in this Hamiltonian. That could be a very interesting and valuable tool. But the current, say, quantum systems we have you get this probabilistic output, so it's very hard to verify such a thing. So could you maybe talk about the feasibility of doing analysis like that?
Yeah, it's a great point. So basically, even if you have the ability to confirm that you have this, that NP has this ability to decide whether or not the formula is satisfiable, it doesn't mean that you can give an efficient witness to show that the formula is not satisfiable in the no case. It just means that no witness will trick you. And so the class of problems where no instances have an efficiently checkable witness is called co-NP, the complement of NP. And SAT is in NP, but it's not believed to also be in co-NP. An example of a problem that is in both classes is factoring, because if there is no factor less than, say, some m, then Merlin can prove this to you by giving you the list of all the correct factors. and then so that's a witness for the no instance. Now, if you have a SAT problem, maybe you can find two clauses. The simplest case would be finding two clauses that just explicitly contradict each other. You know, they could only be satisfied if these two clauses, if a variable is both true and false at the same time. So there are cases where you can give a witness, and certainly in practical SAT solving, you know, you'll have these cases. I'll just mention, I won't talk about it today, but in theoretical computer science, there's something called the sum of squares hierarchy, which is really about, you know, if you can say write your equation constraints as a bunch of squares of things, then for example, you know this, say a bunch of squares plus a positive integer, then you know that you can't have, you know, have this zero assignment because you're adding a bunch of positive things together. So yeah, this is kind of a big topic, but the short answer is there's no general solution for proving that for giving a concise witness that a SAT instance is unsatisfiable, and we don't expect such a general concise witness to always exist.
Yeah.
Yeah.
And by extension, it wouldn't be obvious to make that evaluation in the Hamiltonian.
Right, yeah.
So we have a question from Kunal. So he's referring to maybe the second to last sentence in this complete slide, this last slide,
Sure.
which says this conveys that NP is not all powerful, which is crucial to making it interesting.
Yeah.
So could you just expand on this a little bit?
Okay, sure. So, you know, if NP could solve all the problems, you know, that there are, then perhaps it wouldn't be. So the idea is you can define extremely powerful models of computation once you allow yourself to consider things like, does there exist some witness? And, you know, for example, like a powerful class is p-space, where you have unlimited time, but only polynomial memory space to work in. And p-space contains NP because you could take your unlimited time and search over all possible witnesses until you finally found one that worked for you. But you know, not everything that you could solve in unlimited time and polynomial space. So for example, you could if you had polynomial space and unlimited time, you could confirm that a SAT instance is not satisfiable by going through all possible assignments and finding that none of them satisfy the formula. So p-space is more powerful than NP, or we strongly believe that it is. And as you define these more and more powerful, you know, classes, the question is, what are they telling you about us in the real world, right? So NP is kind of like this really, I mean, it's a nice class for several reasons, that it has complete problems, that it captures so many combinatorial problems, and that in some sense, in the grand hierarchy of everything, it's not that far above P, right? It's something that us mere mortals with our finite time and finite memory can still interact with. So that's, I guess, part of why P is interesting, or NP is interesting.
Great, thank you. We've got quite a few questions coming in now. So next one is from Yeet, and he says, in the class which proofs can be exponential in size, does one also assume the verifier circuits are exponential, or is there a way they could be polynomial?
So I guess you need the verifier circuit to also be exponential in order to even have time to look at the entire gigantic witness that you're given. But you could define kind of a reverse version where you had exponential time, but witnesses of only polynomial size, I suppose. I'm not sure if that has a name, but yeah, so one thing is that the circuit size is at least as large as the witness, just so that you have time to look at the entire witness.
Joe asks, early on you explained the classical Ising model is easy, but when you add this transverse field, the ground state becomes quantum and it's very hard to solve. As you increase the strength of the transverse field, is the transition between classical and quantum regime sharp or smooth? And is this type of transition typical?
It's a really good question. So as we'll see in the next lecture, so in the classical setting, because all the terms commute, you can just assign integers to the energy values. But of course, in the quantum setting, your energy eigenvalues could just be real numbers. And so you can kind of run into precision issues, and we'll discuss this more in the next lecture. But so if you want to talk about the complexity of, say, determining the ground state energy of this transverse Ising model, then you also want to give yourself some precision parameter. And once you do that, so you're just trying to approximately determine the energy, right, up to some finite number of digits. And once you do that, you could get to a case where, well, the precision parameter and the complexity kind of interplay with each other. But yes, I mean, if you made the transverse field very, very large, then you would know that the all plus bit shearing would be a approximately pretty good solution, right? So that's the sense in which you could get there. And because this particular model is exactly solvable, just this particular one-dimensional transverse Ising model, in fact, it's in P, or actually you solve it in constant time because it's just one specific model that you can write down the solution to for all time. And just to kind of maybe belabor the point, I put these, people say the Ising model, they mean all kinds of things, and we have to kind of be precise here. So on this slide, I was just talking about classical 1D ferromagnetic, but of course we call it the Ising model for short. So some Ising models are hard to solve, others are trivial, or nearly trivial.
And one part of the question was about a phase transition, sharp or smooth.
Oh, sure. So, I mean, it's hard to talk about for this particular model just because, yes, we know where the phase transition is. I wrote it down at the critical point so that I could make this statement about the solution being highly entangled. If this part is large, then the ground state is approximately classical. You're in the ferromagnetic phase. And if the transverse term is large, then you're in the paramagnetic phase. Now, suppose you put something much more complicated here, like those max cut cases, with the plus and the general graph, then you could have a significant amount of complexity in the regime where these ZZ interactions are large. It's a slightly tough question to answer. The notion, I'll say one related thing, which is the notion of phase transition does arise in SAT problems. If you think about, if you have a SAT problem with only just a few clauses, then most of the variables are unconstrained and you definitely have a solution. As you add more and more clauses, they rule out more and more solutions. Eventually you add so many clauses that the thing is over-constrained and there's no solutions. So there's actually a point where you have a phase transition from lots of solutions to no solutions at all. And it's a lot of very sophisticated work still ongoing in the past decade to make that phase transition in SAT problems sharp. So this notion does come up, and it's related also to like average case complexity. At the phase transition, you typically have just a unique solution, and average case problems at the phase transition are hard. But yeah, this stuff is a lot more advanced, and I'm not able to cover it today.
Great. Next question is from Zach, and he says, I recall 2SAT falls into P. Is there an intuitive reason why 3SAT is such a substantial increase in difficulty?
Yeah, well, it's correct that 2SAT is in P, and the best reason I can give is just that, where do I say it? That 3SAT is the minimum you need to describe universal circuits that have 2 inputs and 1 output. Yeah, so this piece here, right? So that's kind of why you need clauses that involve at least 3 variables. Now, that's not a proof that 2SAT is easy, right? That's, you give an explicit algorithm for it. But yeah, that's kind of the intuitive reason why you get such a big jump. right? What kind of circuits could you describe with only 2SAT? Would just be wires where you have one input and one output. So that's the intuition.
I might follow up that question with a thing I often forget is that max 2SAT is hard, so you can consider these maximization variants of all these satisfiability problems where you ask how many clauses can be satisfied in a potentially unsatisfiable statement. And even for the case of 2, it's hard, which is pretty interesting. It connects with the Ising models and all this other stuff.
Yeah, thank you for bringing that up. And that's another point to make there is that it's really the frustration, the fact that you can't simultaneously satisfy all the clauses that makes those hard, as opposed to something like if you only have to determine whether they're all satisfiable or not, then you can imagine algorithms that just sort of proceed through the clauses in order and stop when you run into a problem. But if you have to hold in your mind that some of them will never be satisfied, at the same time, then it can get a lot harder. So thanks.
Great. Kunal, Joe, and Zach say thanks for the excellent answers to their questions. I'll give maybe 30 seconds for new questions. Otherwise, we will adjourn this. The next lecture will begin at 11 o'clock, so about 15 minutes from now.
The next lecture will be more quantum.
I would summarize this lecture as a fantastic introduction to CS complexity theory from a physics perspective.
Well, thank you.
Now we can do the quantum stuff. Great. With that, we'll adjourn, and we'll see everybody back in about an hour. Virtual applause all around. Thank you.
Thanks, everyone.